Thank you very much, Wendy, for sharing that. It's one thing I love about the whole energy thing. Sometimes things are a lot easier and simpler than you think, and it's not necessary that you have to always run for the technology solution, but just when you interrogate the system a bit, you can come up with very simple solutions that don't necessarily cost a lot. And that's your winner that you want to isolate, so that and get a quick win out of that then can show the benefit of doing energy efficiency in your plant, and then give you the ammunition to go back to management to motivate for funding for the more capital intensive investments that you might need to make. So thank you for that. I think while we were doing the session, there was a question about the case studies, and are there case studies available from state-owned entities? I think there are one or two, but I would urge anybody interested in knowing more about the case studies, please visit the website, because all the available case studies are actually posted on there. If there isn't one there, you can contact NCPC and we'll see what we can assist you with, whether there's one that maybe hasn't yet been published. Okay, I also just wanted to note that what we're also seeing from what Wendy presented, and the fact that she was also providing support and services to UNIDO internationally, and attending and making an impact at breweries overseas, and that's also something that we've prided ourselves on. And I think it was something I highlighted in my talk this morning, that more and more of our experts and specialists are starting to get international recognition, which I think must be a testament to what the project has actually done, and how we've gone about supporting these specialists and assisting them to play in the space that they are embarking on now. So with that, I'd like to welcome our next speaker. This will be Professor Rens, and he's from the Northwest University, and I believe Prof will be sharing with us a little around how end users of electricity can actually contain poor voltage quality. So this brings in the whole concept of power quality. So Prof, thanks very much for being here, and the floor is yours. Moving forward, it's the wrong way around. That's the forward and back button. Okay.
Thank you, friends, and a few that is still attending. The good news is it's going to take much less time than was advertised. The bad news is I'm doing it in a foreign language, so bear with me. But nowadays, I know some words in this language. What it is about, this active voltage conditioning, and listening to what Wendy was saying, I was also wondering how energy efficient those plants are when the power is off, electricity is off. Because I think that could affect all that cost savings. No? Without electricity, nothing is happening. And in this country, we can predict, well, I can predict with quite certainty, that in the future electricity will cost more, it will become more unreliable, and the quality will be worse. Now, quality, sometimes referred to as power quality, voltage quality. Voltage quality is a DHL vehicle that brings the energy to your plant, but if that quality is not good, your plant will also not be that happy. Now, we can do something about it as end users, and that is the story I would like to tell. So firstly, I will motivate why it is so important for end users of electricity to realize that although we've got a NERSA sitting in Kuvalulu House here in Tshwane, Pretoria, not looking after the quality of the product being sold by municipalities, by Eskom, whilst they take your money, selling you water, you would like to know that this water is consumable. They sell you electricity without you knowing that it is good enough for consumption, but you pay the money. but they don't look after our interest quite well. Then I will tell you how we can improve the business and operational risk that results when we consume that poor voltage quality. You can imagine one of the motor manufacturers around here, when voltage quality is not good, they operate a long serial production process. When something makes that robotic arm stop, that scheduled production of, in this case, 320 luxury German vehicles can't be realized during that day. And with each of those vehicles costing nearly R1 million, you can imagine the impact on only their economy. So I'll show you that, referring to my German example, there are solutions. And the one that's at the moment my favorite is from Germany, Vorsprung durch Technik. And I'll show you a Southern African case study on how well it can be done. I have the privilege not only being an academic, the similar scenario is you can't really teach someone to play rugby if you don't play rugby yourself. Otherwise, you just become a Blue Bull fan sitting on the pavilion and commenting on what should be done. So I have the privilege to being involved in industry as well. So let's look at a few concepts. Important to appreciate how well power electronics have advanced during the past 10 years. We can now handle very high voltages and currents simultaneously, control them very accurately at very high speeds, and with signal processing be as powerful as what we, for example, can see in a cell phone even nowadays. It is now possible to do really impressive processing of electrical energy. So the idea is that where we consume the electricity, initially the idea was, and that is how NERSA perceived it, that the product being injected into the network, coming off the coal-fired power station, that would have been beautiful. That is excellent electricity, although the greenies don't like it. But the quality of that voltage is excellent. And the idea was that as it flows through the system up to the point of consumption, that you will know what that quality is and at least make sure that the end user get it at an acceptable level. I'll later on talk about what is sufficiently good or when electricity is sufficiently good enough. So the solution which I like comes from Germany, although the Chinese is already trying to do the same. There are some Canadians, and I haven't seen good solutions from America yet, but those solutions that I will show to you aims at the end user. With the end user, the water is at least there. You can take it and condition it to the state where I'm happy to drink it. The same can be done with electricity. And I'm not talking about a double conversion UPS. I'm talking about a much more sophisticated and maybe even simpler solution. So let's do a brief overview of what power quality is about, and that is also how my relation with NCPC started, where I helped them to develop a few courses and presented it. Now, power quality, you can say, include both the effect of voltage and current, and of course, if both are there, we talk about power. So the idea is to qualify and quantify the quality of electricity. With the concepts behind them, there are a little bit of network principles involved, but power quality is defined formally, for example, in standards. So the idea is that the utility will supply a voltage signal to a consumer. The consumer will draw the current, but a poor voltage will supply a poor current. But unfortunately, this is a difficult business. You're buying from a Spar or any other shop, and you are a poor customer and you affect the quality of the product the shop is selling to you. That doesn't sound right. But that can happen with electricity. Some customers, the furnaces that Wendy referred to, they are quite a big culprit in damaging the voltage quality in the network and other consumers can also suffer. So it is a difficult business. But in this, unfortunately, sits the reality of electrical networks. And I call this constant law of misery in power systems. And a clever guy, Ohm, has defined the relation between voltage and current when there are not an infinite impedance involved. We can measure it in ohms. If we haven't had any impedance, the voltage signal going into the network would have remained perfect, regardless of how poor the current looks like that's being withdrawn. I don't have an idea of the background of you people and how technical you are, but I'll try and make up for it if you don't know all about this. But there is, unfortunately and fortunately, a kind of a metaphor, and for you that can't read there, it is a lot of message in this, and I use a metaphor quite keenly sometimes, but it says, Sparky, your mother and I are shocked at your current behavior. Until you learn to conduct yourself properly, you are grounded. And you'll see how this literally realizes in the presentation that I do. So electrical power quality in Southern Africa is supposedly controlled by NERSA. I can assure you they're not doing much about it. If it was not for Eskom, all of us would have suffered much more. A few municipalities do power quality, they monitor it and they try to manage it. But if it was not for Eskom, we would have suffered even more. They are really still doing a good job in this regard. The idea was that NERSA would decide who may generate, sell and resell electricity by a government mandate. They do a little bit more than price, or they should have done, but this is not really done very well. They have built some rules into how this whole business should happen, but when there is no policeman next to the road, you can drive as fast as you want, even with the knowledge that you should not exceed 120 kilometers per hour. And this is what is happening at the moment in this country. I'll go a little bit fast here and there, but please read where I'm maybe not emphasizing some of these points. The fact remains that today electricity is an important commodity. It's even recognized by the law, by the courts of law, for the reason that initially some clever lawyer said during a case where electricity was stolen, okay, show me what was stolen. And what was stolen? I don't know, it was stolen. I can show you there were wires across the meter. Yeah, but what was stolen? You can see the dilemma. And it took some legal arguments to convince the courts that it is a physical commodity similar to water. There is sufficient laws and principles to define what electricity and electrical energy is about. But you see, that is where we're going. In our system nowadays, you will agree that the impedance is probably quite compromised. We don't have sufficient network capacity. Networks are not upgraded. Transformers are not upgraded. More lines are not built. And the idea of the utility really is to get that current to the end user, but at that end user, due to the degradation of the voltage quality, we need a solution to keep business going. So how can those end users be protected? A long sentence here, but the idea is that we can contain our business risk sufficiently if that electricity is not compliant to the minimum technical requirements. Now, this kind of solution is very attractive, but very hard for people to make them understand and appreciate that it is possible. This one car manufacturer here in your area in Roslyn has done this, and they have significantly increased their exposure to business risk by doing that. So it is possible to do some kind of local control over the quality of the voltage being delivered to you. Equipment is not that immune. In this case, immunity of compressors, and I have heard when he talks about compressors, was very important, the reliability or the availability of those compressors, because if the compressed air into those robotic arms are not sufficiently controlled, the robotics arms stop, not due to an electrical problem. Now you can see we are 2 arm lengths away, because in between there sits a compressor. But the compressor that fails or shuts down, it doesn't fail, but it takes a process to restart it, cause the robotic arms to stop. So simply by protecting the compressors, that they don't stop, the plant could have already increased its availability significantly. So the idea is not to create a perfect world. We want to create a scenario where the electricity is sufficiently good and supply our equipment with electricity being sufficiently good. It doesn't need to be perfect. We just need to keep them operating very reliably. Now, what sufficiently good electricity means, that could also be quite complicated. And the metaphor here is, unfortunately, that it is hard to assign the responsibility for the different issues that goes wrong in this process. And sometimes it is literally the case like where this guy is concluding, I need to blame my upbringing. And part of that lack of knowledge and understanding, I would like to think that is served by NCPC. The problem is that we can't hold our suppliers fully responsible for what is going wrong. Sometimes we as the plant owner or operator are also partly to blame. So I'm not going to go in all the detail of this, but basically what I'm dealing with is described here, and what is encircled in red at the moment is not what I'm dealing with today. I'm dealing with voltage magnitude, voltage unbalance, harmonics, and a flicker, dips and swells, and how we can get rid of them, or at least improve them significantly. The traditional UPS that you probably know sits there on the left-hand side. It can take care of the interruption, having batteries where energy is stored, and when grid energy is gone, it can supply electricity. But this is something different that we're dealing with in another context, not here. So today, that what is left there, I will quickly refer you to. The idea is that we can now, with the technology being available from Germany, as I have already mentioned or hinted towards, serve any load with a perfect voltage magnitude, regardless of loading. No voltage drop should concern you in the supply network. Regardless of the variations in the supply network, acting as an extremely fast tap changer, at least 10% above and below the nominal value. Now, let's say the example that me and Tanya is at the moment looking at, the voltage sits at 10.5 kilovolt. The client expects at least 11, but imagine that is the in-feed to a plant. There will be some voltage drops downstream. So his equipment is already below an ideal voltage. The motors sucks in more current because voltage is less. They run hotter, they don't last. And many other problems can arise. That voltage can be boosted by at least 10% continuously to a value of 11 or 10.5 plus another 1,000 volts. So we can boost it easily to 11.5 roughly. Or if voltage is too high, even reduce it continuously. And that is not done by an UPS. What is so beautiful about these solutions and these very, very fast power electronics and signal processing nowadays available, it can be done per phase, of course, but also in terms of phase angle. A three-phase system, I think most of you will know that, should have an offset of 120 degrees between phases. If that is not perfect, That asymmetry also affects the operation of equipment, long stories behind it. But the point is, we can end up with a 0% voltage unbalance. Don't worry too much about flicker now, but you will also have no flicker. And that is basically an effect which will cause irritation in people like you sitting in a room like this without sunlight, where the lumens production of the lamps are being modulated at around 8.8 hertz. You will not notice it. Your eye will not tell you, but you'll get a headache, you'll feel irritated, you'll get a migraine, you can even get epilepsy attack if flicker is bad. In Pretoria, I don't expect it be too bad, and these kind of lamps that you see here, these gas discharge lamps, also dampens the flicker a little bit. But the LED lamps are nowadays bringing flicker back. But that is a story that's not for now. We can do all of this nearly and instantaneously, 1.4 milliseconds. Now consider a 50 hertz signal, 20 milliseconds each wavelength. So if you can fix up that voltage waveform in 1.4 milliseconds, the equipment will not know this, and that is done without batteries, without storage. So there is the typical solution, shown here already, the robotic arms. And I just have added there that on their description in the German, they didn't translate it very well, but it means literally that one can realize, and that is where business risk for a lot of the industry in Southern Africa sits, to realize uninterrupted production. That could be beautiful. And this is done by really fast voltage mitigation, which I will get to. So what is done? Let's look at a typical example of a voltage dip. Voltage in this case sits at any value. Let's make it a 10.5 kilovolt. And somewhere in the network is a short circuit, so the voltage just drops off. Normally this is how it happens, very fast, and it will recover a bit slower. But there's a period of time where, per definition, when it goes below a certain threshold, it will be defined 10% below the nominal. If that is 11 and that is 10.5, so that will be at 9.9 kV. If voltage drops there, it will remain there until the fault in the network is cleared by some breaker. Some overcurrent protection clears the fault. Now the voltage just recovers back to the value it was before the dip occurred. So for a period of time, a duration, we lose, in fact, some energy being served. That is what makes equipment stop, or your TV at the home being reset or switching off. So what is needed is to take any condition, which is shown up here, where the amplitudes are not the same, they're not even symmetrical, to such a scenario. And that is what we will realize here. I'm not going to go into this because this is not a power quality course, but just briefly, what is happening? Equipment should survive by being more immune than what the grid is bringing. So you can imagine what we see here. This fancy German car that requires 50 parts per million in terms of the diesel you would like to buy. And some of them are clever enough to know if you put 500 parts per million, but there's not available, luckily, anymore that much, the 500 parts per million, but the car is not compatible when the, let's call it, contamination in the fuel is too high. We see it with electricity as well. There is a certain level of contamination defined by a range of parameters where up to that point the equipment should be okay. But above that, unfortunately, it is not, and it is costing our industry a fortune. So how it is done, there is an example to explain that what we would like to achieve is when that voltage sag, for example, occurs. But it could have been too high, too low, permanently, many other issues, but I'm just using this example. There is a grid, supply impedance. We would like to just fix up that part We don't want a UPS that takes 100% of the energy, store it, and then convert it to the perfect. That is not needed. There's just something wrong and not that much, and we fix it instantaneously. We could realize that stable voltage. And this is done by taking energy from the supply system. There is a control system that by using this transformer instantaneously can inject this. Right, so there's a UPS example, and let me be quick. We'll lose 10% of the energy coming off the grid to supply you with about 90% of the energy continuously. This is about the losses that one can expect when you convert all of the energy through the power electronics. But this device will cause an energy efficiency in real life nearer to 99%, but I've written down 98% here, by only taking the part of the energy that's not correct and instantaneously fix up the voltage signal, and it costs much less. And I will not go into all of the detail here. If you are interested, my email was also somewhere. You can always contact me. But let me show you now a practical example. What you see here is not a teenager with a skin problem. What you see here, each red dot, is when voltage was out of bounds, being defined by a technical standard, being either too high or too low for a certain period of time. Time is on this axis logarithmic. There is a reduction in voltage. The idea is voltage should remain within 110 and 90% of the value that is regarded as nominal. So the variations should sit here, and that is how networks should be operated. But faults occur, and this was not over a very long period. But each of them is an incident where a so-called dip is measured due to a short circuit somewhere. We are interconnected. A fault can occur down in Johannesburg, where they repatriate the towers, transmission towers. The line falls over, but you will see it in Pretoria, because it's a high voltage line causing a huge fault current. And that incident on that day can make the plant stop. Now, if every one of those, at least those, not that sitting there, at least those, causes a plant to stop, to cause 50 BMWs, oh, there I've mentioned them, not to be produced today. You can imagine what old Hans and Horst am Deutschland is doing. They want to make money. They're not here because they are missionaries. And they've promised the BMW to be delivered. And now they've got a reputational risk resulting. So this is not acceptable. So you must do something about it. Well, you can generate your own energy, but that's not to be done. So there is, sorry, I must just go back one. This is the before and after scenario. This was luckily not BMW. This was a case that's much worse. But although it seems that some of them are remaining, some of them could not be fixed, some of those ones were ones from the previous slide that were boosted higher, but still fell in an area where it's potentially dangerous. But you can see how few of them remain. And this is measured data. Data that I can validate at any time, field data. This is much better. So we have improved our business and operational risk from a dip point of view already significantly. Unfortunately, the lines here are not that visible on what happens during the dip here due to the resolution of the screen. But at least here you can see that is where the grid voltage sits, and it was too high. This is the output voltage. So I've measured the input voltage to coming from the grid, the output voltage going to the plant, and you can see it looks already much better. And during the dip condition, doesn't matter about the detail, it was boosted back, and this is just a real measurement on what happened. So don't worry too much about the detail because the resolution is not that good here. The point is, it happened instantaneously, near instantaneously. You can't even see the delay there. That is how fast the power electronics now can do this. There is a waveform measured, and now you can see it much better. The waveform was not perfect. The blue one is showing the affected voltage, and there is the voltage that's being fed to the equipment, and you can appreciate that the equipment is riding through this. This one, just to demonstrate phase angle, one would regard phase angle to be fixed, and this is from the grid during a fault. A phasor, for you that are known to this concept, can jump up and down. In other words, they are not perfectly displaced at 120 degrees and not perfectly stable, and only that can make equipment stop, not only the change in magnitude. But here, look here how fast it is compensated. When the phase angle jumped, that line is going to the plant. So this is much more acceptable. This is just to show, and this is not bad voltage regulation. In this case, there's a technical standard to tell you how good voltage is, but it was assessed over a period of time to change roughly 6%. Not too bad, it's not wonderful, but it's acceptable. But look here, on the output of the device, not even 1%. So you can really keep the voltage perfect. End users who are exposed to the current scenario in South Africa. Voltage unbalance here, not bad. It's not bad. This is not too bad. But look here what happened when it was compensated. Now it is really perfect. In terms of voltage magnitude, there is the before and after. There the device was switched on. And you can see their voltages are controlled perfectly. This is a case where voltage was too low. Now it's permanently boosted. This one, it's a little bit hard to see. Let me skip this one. Voltage unbalance, not too bad, but after the device being switched on perfectly. The previous one, in which I can't really show the detail, you must realize operational or business risk is not only about making money. Pumping water, Rand water, if the pumps are not reliable, the water pressure, the water flow in the system is not reliable. So sometimes it is about the strategic value that sits in reliable operation of equipment, serving, for example, water, handling sewage, and all of them needs electricity of sufficient quality. And that can be done. There is just an example of another voltage unbalanced one. Was not too bad, but there you can see how well it was improved. So in conclusion, end users can really nowadays find solutions to themselves, take care of what is happening in our grids. We don't have to complain only. Of course we should, but it can be done in a sensible way in terms of the investment. Return on investment can be built into a business case, and one will often find, and I only have done 3 cases here, that it pays for itself quite soon. So although the future seems not too exciting in terms of what is happening in our networks, I would perceive the most important message of this afternoon is that solutions are available without the expense of a normal UPS and the maintenance requirements of batteries, where one can condition the voltage to a sufficiently good level where your equipment is connected up to a few MVAs, up to 22 kV, but it's not really necessary. One should rather distribute these kind of solutions throughout the plant and make sure that the sensitive equipment becomes predictable in terms of the scheduled production cycles. All right, so that is it. Thank you then.